every ultra-fast optics lab needs to have a pulse compressor. There are probably about 1,000 ultra-fast optics labs in the world, and there are lots of industrial ultra-fast optical setups. Ultra-fast optics are being used in a wide range of applications, from micromachining to medical imaging to ophthalmology even. And so it's very important to be able to maintain the pulses short. And right now, people, in fact, several laser companies just sell people longer pulses than they would otherwise benefit from because it's so difficult to keep them short. But with our device in the beam, and it's easy enough to work with now that anybody can use it, so anyone can now use shorter pulses, pre-compensate for any glass that the pulse goes through. Almost every pulse is used at a focus, but to get a good focus, you need a lens with a lot of glass in it, and that glass makes the pulse longer. But we can stick one of our devices in the beam before the lens and compensate for the glass in the lens, and get the shortest pulse and hence the highest intensity at the focus. In the field, it's very important to be able to control the pulse, to shorten it, to compress it, and also to be able to measure it. Swamp Optics was formed to develop devices and sell devices that actually measure the ultra-short pulses, to measure their complete intensity and phase as a function of time. And we developed a technique called FROG, frequency-resolved optical gating, to measure it. We also developed a simplified version of FROG called grenouille, the French word for frog, which is a completely simple, hands-free, auto-aligning device that also measures the intensity and phase as a function of time, and it's cheaper. What was interesting, though, is we discovered that grenouille also measures some spatiotemporal distortions that plague the field, such as pulses propagating at an angle rather than straight, and spatial chirp, where the red is on one side and the blue is on the other. And when we used our grenouille out in the field to measure pulses and sold lots of them to customers who then used them, we discovered that nearly every pulse was contaminated with these spatiotemporal distortions. And we wondered, where did that come from? Well, it turns out that it came from the pulse compressors that people were using to compress the pulses after they propagated through glass. And that's because these compressors had 2 or 4 prisms in them, and the prisms could very easily misalign. The beam had to enter each prism at exactly the same angle, or else you would have these distortions. And people would have significant amounts of these distortions, all coming from the compressor. So we decided, let's invent a better pulse compressor. So we thought about it, and we decided that more than one prism was unacceptable. Yet every pulse compressor had 2 or 4 prisms in it. So we built one with 1 prism in it, and it involves a precisely manufactured corner cube to pass through the prism. In fact, we passed through the one prism 4 times, and the corner cube guarantees that the beam always goes through the prism at exactly the right angle. And what we found was that this device, as simple as it is, in fact, probably because it's simple, it actually completely compensates for all of those distortions. There's no way that you can have any of those distortions in your beam. And because the device is simple and easy to align, we can manufacture it very cheaply. So our device not only is completely distortion-free, but it's also half the price of competing pulse compressors. And then in addition, it turns out we really only need 1 model for each wavelength, because it can also compensate for, at the same time, beams with large bandwidth and beams with small bandwidth, devices that, or situations that in the past have required separate devices. So it's very nice. Everything worked out for it. It's a nice and innovative device, and we're proud of it, and it works very well.